Hello students, today we are going to see the continuation of sample paper 2017. So in this paper, we are going to discuss the chapters related to circles and area related to circles. So in circles, we are going to use a theorem, the tangent drawn from an external point to a circle are equal, and as well as a tangent is perpendicular to the radius through the point of contact. So using these two theorems, we are going to solve the problems. Also in area related to circles, we are going to find out area of the shaded region which was present inside a circle. So we are going to see now. Today we are going to discuss about the continuation of sample paper 2017. So here we are going to discuss about the chapters circles and area related to the circles. First, we will see circles. Under circle, we have the topic tangents to a circle. We are going to see the theorem which is related to the tangents to a circle. So, in the sample paper, he will be asking this theorem to prove, where the theorem states that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So, I have drawn a figure here, a circle with center O. I have drawn a radius OP and I have drawn the tangent XY. So, the tangent touching the circle at the point P. So, my XY is called as a tangent. So, I am going to prove that OP radius is perpendicular to the tangent. So, let us come to the proof here. Given a circle with center O and tangent XY to the circle, we need to prove that the radius is perpendicular to the tangent. That is, OP is perpendicular to XY. So, here I am going to take some other point, naming it as Q on the tangent line XY. So, where this Q, you should be aware that the Q should lie outside the circle, not inside the circle. If Q lies inside the circle, this XY line will also lies inside. Then this XY will not become a tangent. When it lies inside the circle, it becomes a secant to the circle. So, we are just keeping a point Q on the tangent line XY. So, I have written here, take a point Q on XY other than P, join OQ. The point Q must lie outside the circle, because if Q lies inside the circle, XY will become a secant to the circle, not a tangent to the circle. So, from this figure, I find that OQ will be the largest distance of when compared to OP. So, here I am writing OQ is greater than OP from the figure. So, this happens for every point if you mark on your XY, that is except your point P. So, I can say that if you take any points on the line of the tangent which is lie outside the circle, those distance will be greater than the distance of OP. So, from this I can say that OP will be the shorter distance when compared to other distances. So, hence I can say that OP forms the perpendicular line to my tangent XY. So, here I am writing OP is the shortest distance of all the distance. So, OP is perpendicular to XY. So, here we are going to use this theorem in many problems to solve it. First problem, prove that the length of tangents drawn from an external point to a circle are equal. So, he asked you to prove that the length of the tangents drawn to a circle are equal. So, this is stated as a theorem in our textbook. So, I am going to prove this. So, for that I am drawing a circle with center O and I am taking an external point T. From T, I am drawing the tangents to a circle TP and TQ. I want to prove that TP length is equivalent to TQ length. So, here I am joining OP and OQ, where OP and OQ forms the radius of the circle. Also, I am joining OT. So, here I am going to divide this into two triangles by the line OT. Now, coming to the solution, I am going to consider triangle OPT and triangle OQT. where my angle P and angle Q forms 90 degree because of the theorem the tangent is perpendicular to the radius through the point of contact, where P and Q are the point of contacts for the tangents TQ and TP. So here I am writing this as angle OPT is equal to angle OQT, which is equal to 90 degree. So I can say that the triangle OPT and triangle OQT are both right angle triangles. So I can suggest that using RHS congruence, I can prove that the length of the tangents were equal. So for RHS congruence, I should prove the hypotenuse of both the triangles and one side of the related two triangles must be equal to each other. So in triangle OPT and triangle OQT, we find that OP is equal to OQ. So I am writing the reason, radii of the circle. Similarly, so this OP and OQ forms the related sides of these two triangles, and OT will be the hypotenuse of the triangle OPT and triangle OQT. Also, it forms the common side to both the triangles. So, my second point is OT is equal to OT. Since OT forms the hypotenuse to both the triangles, I am writing this common hypotenuse. So, I find one side and one hypotenuse of triangle OPT and one side and one hypotenuse of triangle OQT are equal to each other. So, by RHS congruence, triangle OPT is congruent to triangle OQT. So, here I found that the two triangles are congruent to each other. Therefore, the related sides PT and QT are the corresponding sides of the two congruent triangles. So, I can relate the length of PT is equal to QT by CPCT. That is corresponding parts of congruent triangles, where PT and QT are the two tangents drawn from an external point T. So, I proved that the length of the tangents drawn from an external point to a circle are equal. Hence, I proved this theorem. Second problem, a tangent PQ at a point P of a circle of radius 5 cm meets a line through the center O at a point Q. So that OQ is equal to 12 cm. Find the length of PQ. So, with a given statement, I am going to draw the figure. So, I have drawn a circle with center O, and he is talking about the tangent PQ. So, I have drawn a line PQ. I am going to mark a point P and Q. He was talking you that the tangent PQ, which was drawn to a circle, touching the circle at a point P. So, I am just naming this point as P, and here the external point I am naming it as Q. Also, he has given that Q, this external point, is joined to the center of the circle by a line segment whose line segment length is 12 cm. Now, we need to find out the length of PQ, that is your tangent length. So, we know that by the theorem, the tangent is perpendicular to the radius through the point of contact. So, my angle OPQ is 90 degree. By using the Pythagoras theorem, I can find the length of PQ. So, now coming to the solution. So, I am writing that we know that the tangent is perpendicular to the radius. Through point of contact. So, angle OPQ is equal to 90 degree. So, by now we are considering the triangle OPQ. So, I am going to use, I am writing angle OPQ is equal to 90 degree. So, by Pythagoras theorem, we know that the hypotenuse square is equal to the sum of the other two squares. So where the side which is opposite to 90 will be the hypotenuse. So I am writing OQ squared is equal to OP square plus PQ square. So which implies OQ will be, hypotenuse will be 12 square, which is equal to OP will be 5 square. So we want to find out the PQ square. From PQ square I can find the length of PQ. So where 12 square is 144, 5 square is 25. So bringing this 25 to the other side, it becomes a minus 25, which is equal to PQ square. So which implies 119 is equal to PQ squared. So further PQ is equal to square root of 119. So I got the length of the tangent PQ as root 119. Third problem. Prove that the tangents drawn at the ends of the chord of a circle makes equal angles with the chord. So I have drawn a circle with a center O, and TP and TQ are the two tangents touching the circle at the point P and Q. And I have drawn the chord AB where this touches the circle at A and B. Now I am going to join OT such that this OT touching the chord AB at M. I need to prove that the tangents drawn to the ends of the chord makes an equal angles with the chord. So here I need to prove TAM angle A, that is TAM angle is equivalent to TBM angle. So now coming to the solution, I have written AB is a chord, PT, QT are tangents, join OT such that OT touches AB at M. Now I am going to consider the triangle ATM and BTM to prove the congruence here. So we are considering ATM and triangle BTM. In order to prove that these two angles are equal, where these two angles are involved in this triangle. So first case, I find that in these two triangles, MT is a common side. So I have written MT is equal to MT common side. So the next case, we know that the tangents are equally inclined to the line segment, joining the center with the external point. So I can say that angle ATO, so I am just taking this O as a point M. So ATM angle is equivalent to angle BTM. So I am writing here angle ATM is equal to angle BTM. The reason is the tangent line inclined, where this tangent line angle which are equally inclined with the line OT, where this OT line joining the center of the circle with the external point. So I got one side as a common side in both the triangles, and angle ATM and BTM which is involved in these two triangles are equal. Now the third side I want to see here, where AT is equal to BT, where A and B lies on the tangent line PT and QT. Since my PT and QT are equal, where the tangents drawn from external point to a circle are equal, I can say that AT will also be equivalent to BT. So I am writing AT is equal to BT. Tangents drawn from some point to a circle are also equal. So I got two sides, one angle. SA is congruence. Both the triangles are congruent. So ATM, BTM are congruent. That angles, that is your angle TAM and TBM, where these two angles are involved in the two congruent triangles. So by CPCT, I can say that the two angles are equal. So I am writing the reason CPCT. So I got TAM angle is equal to TBM. Thus by proving that the tangents drawn at the ends of chord of a circle makes equal angles with the chord. Fourth problem, in the given figure, XY and X dash Y dash are two parallel tangents to a circle with center O, and another tangent AB drawn to a circle which intersects at the point C, and this tangent AB touching the parallel tangents XY and X dash Y dash at A and B. So we need to prove angle AOB is equal to 90 degree. So he has given the figure where XY, X dash, Y dash are two parallel tangents to a circle with center O. Also one more tangent AB is drawn to the circle, touching the circle at C, where this tangent is touching your parallel tangents xy and x dash y dash at the point A and B. I want to prove that angle AOB is equal to 90 degree. So now we are going to have a solution now. Now coming to the solution, we are going to take first the triangle PAO and the triangle COA. So consider triangle PAO and triangle CAO. So I am going to consider these two triangles. I am going to prove that these two triangles are congruent to each other by previous theorem, that is the length of the tangent, that is your tangent is perpendicular to the radius through the point of contact. So I can say that OP is perpendicular to PA. The reason is tangent is perpendicular to radius through point of contact. So I can say angle OPA is equal to 90 degree. Also, so if I take this C as the point of contact, where OC is the radius of the circle, and we know that AB is a tangent touching the circle at the point of contact C. So I can say that the radius is perpendicular to the tangent through the point of contact C. So my C will also becomes 90 degree. So I am writing OCA as 90 degree. So also angle OCA which is equal to 90 degree. So we are considering now in triangle OPA and triangle OCA, we know that angle OPA is equal to angle OCA is equal to 90 degree. So I have taken these two triangles I shown by the shaded part. So first case I have OA. OA is the hypotenuse to the triangle OPA and OA is also the hypotenuse to the triangle OCA. So my first point is OA is equal to OA common side, where this common side forms a hypotenuse for both the triangles. Now second case, I got OP is equal to OC since they are the radius of the same circle. So I am writing OP is equal to OC radii of a circle. So by RHS, triangle OPA is congruent to triangle OCA. So which implies angle PAO is equal to angle CAO since these two angles are forms the corresponding angles of the congruent triangles. So which implies angle PAO is equal to angle CAO by CP/CT, that is the angles which are related to the congruent triangles. So the corresponding parts of the congruent triangles, so these two angles becomes equal. I am calling this as equation 1. So I proved that these two angles are equal. Now I am going to consider the triangle OQB and OCB by the same procedure, because your Q is a point of contact for the tangent x dash y dash, and similarly C is the point of contact for the tangent AB. So here my Q and C becomes 90. Similarly, by RHS, these two triangles are congruent. So I am writing the word similarly. Similarly, triangle OQB is congruent to triangle OCB. So which implies angle QBO is equal to angle CBO. Calling this as equation 2. Now I am going to, since I have these two are equal angles and these two angles OAP is equal to OAC, and I need to prove angle AOB is equal to 90 degree, I am considering triangle AOB. So in triangle AOB, I can say that this angle AOB, by using the angle sum property, I have angle OAB plus angle AOB plus angle OBA, which is equal to 180 degree. Now I want to find for angle OAB. So OAB can be got from PAC. So I am writing the point here. XY is parallel to X dash, Y dash. And if I take this tangent AB as a transversal, I can have angle PAC plus angle QBC is equal to 180 degree co-interior angles. Now, these two are parallel tangent. AB is a transversal. So, angle PAB, that is PAC, and angle QBC, this entire forms a co-interior angles. So, in place of angle PAC, I am going to write it as OAC, since my angle PAO is equal to CAO. That is, your angle A has been equally divided into two equal angles. So, I am writing angle A as 2 times of angle OAC plus similarly QBC, this B has been divided into two equal angles by the equation 2. I am going to write my OBC, that is 2 times of OBC as my angle B. So, I am writing QBC, the entire angle QBC as 2 times of angle which is equal to 180 degree. So, now I am taking 2 commonly outside, and if I take 2 commonly outside and if we bring the 2 to the other side, it becomes angle OAC plus angle OBC is equal to 180 divided by 2, which is 90. So, you are having this equation 90 degree. Now, I am going to substitute here. So, instead of writing OAB, I can stop with OAC also. So, for OAB, I am writing OAC, and OBA, I am stopping with C, OBC. So, this together, I got that as where this 2 angle I got as 90 degree plus angle AOB is equal to 180 degree. So, which implies angle AOB is equal to 180. 90 degree goes other side, becomes minus 90, which is equal to 90 degree. So, hence I proved that angle AOB is equal to 90 degree. Next case, we are going to solve the problems which is related to areas related to circles chapter. So, before doing this problem, you should be knowing the formulas for finding the area of the sector, length of the arc of the sector, as well as angle in a semicircle. So, I have drawn a sector. Sector is nothing but the region which is occupied between the two radii with the arc of a circle. So, this region is called as a sector. If I want to find the area of this region, which can be found out using the formula theta by 360 into pi r squared. Second case, if I want to find the length of the arc AB of a sector, I should use the formula theta by 360 into 2 pi r. Next case, you would have studied in your 9th standard level itself. That is, your angle in a semicircle is equal to 90 degree. So, I have taken the semicircle and where the angle formed inside the semicircle. So, I can say that the angle formed in a semicircle is 90 degree. So, my angle C will be equivalent to 90 degree. Fifth problem. Two concentric circles with center O have radii 14 cm and 7 cm. If angle AOB is equal to 30 degree, find the area of the shaded region. So, he has given the figure of two concentric circles with center O. and the radius of the bigger circle as 14 centimeter and the radius of the smaller circle as 7 centimeter. And he has given angle AOB is 30 degree. We need to find the area of this shaded region. So which can be obtained by subtracting the bigger sector. So this resembles this figure. OAB resembles the sector region. So this bigger sector minus the smaller sector OCD. So I want to subtract the area of the bigger sector minus the area of the smaller sector. So I am writing here radius of the bigger circle 14 centimeter, radius of smaller circle 7 centimeter and angle AOB is equal to 30 degree. So area of the shaded region is equal to, you have the formula for the sector, area of the bigger sector theta by 360 into pi r squared, where capital R denotes the radius of the bigger circle. Similarly, radius of the area of the smaller sector will be theta by 360 into pi r squared, where r denotes the radius of the smaller circle. So since we have theta is common to both the smaller sector and the bigger sector, I am taking it as a commonly outside. So theta by 360 as a common, taking commonly outside, and pi also commonly outside. Remaining you have r squared minus small r squared. So I am substituting theta value as 30 by 360 into 22 by 7 into capital R squared is 14 squared minus of 7 squared, which is of the form a squared minus b squared. Further, I am expanding this. So 30 by 360 as 1 by 12 into 22 by 7. This is of the form a squared minus b squared, identity a plus b into a minus b. Further simplifying, I will be getting 14 plus 7, 21, 14 minus 7, 7, the remaining as it is. So further simplifying everything, I will be getting 77 by 2, which is equal to 38.5 centimeter square, which will be the area of this shaded region. Sixth problem, ABPC is a quadrant of a circle of radius 14 centimeter and a semicircle is drawn with a BC as a diameter. Find the area of the shaded region. He has given the figure where it denotes ABPC will be the sectoral region subtending an angle 90 degree. So it is called as a quadrant of a circle. Now with the BC as a diameter, he has drawn the semicircle here. Now I want to find the area of this shaded region. So which can be found out by subtracting area of the triangle ABC plus the area of the semicircle. So I am just adding triangle plus semicircle, and from this addition, that is from area of the circle plus area of the semicircle, I am subtracting this quadrant. I will be getting this shaded region. So in order to find the area of the semicircle, I need the diameter of the circle, which can be found out by this right angle triangle. Since it is a quadrant of a circle, my angle A is 90 degree. So using Pythagoras theorem, in this triangle ABC, I can find the hypotenuse BC, which forms the diameter of the circle. Now coming to the solution, in triangle ABC, we know that angle A is 90 degree. By Pythagoras theorem, hypotenuse square is equal to sum of the other two sides square, where it is given that the radius of the circle will be 14. So my AB is 14 and AC is 14, since it forms the radius of the same circle. I am writing 14 square plus 14 square, 196 plus 196. So I am having this as 2 into 196. So where I got BC square as 2 into 196, BC is equal to square root of this. So 196 take square root, it will be 14, and 2 I am writing it as root 2. So I got BC as 14 root 2 centimeter, which will be the diameter of the circle. Now area of the shaded region is equal to area of the triangle plus area of the semicircle. I will get the entire figure, and from this I am going to subtract the quadrant of a circle. So area of the triangle ABC plus area of the semicircle having the diameter as BC minus the area of the quadrant ABPC. So area of the triangle half into base into height for right angle triangle. So where my base is 14, height is 14, half into 14 into 14 area of the triangle plus area of the semicircle is, area of the circle is pi r squared, semicircle is pi r squared by 2. So pi 22 by 7 by 2 I am taking to the by 2, this denominator 2 comes in a multiplication sign. So it can be written as 1 by 2 into pi r squared. So radius will be, diameter is 14 root 2. So radius will be 14 root 2 divided by 2, which is 7 root 2. So pi r squared is 7 root 2 into 7 root 2 divided by 2. So that 2 I am writing it as into 1 by 2 minus area of the quadrant. So we know that the area of the quadrant, that is a sectoral region, theta by 360 into pi r squared, where radius forms 14. So I am writing 90 by 360. So where 90 by 360, if I simplify, I will be getting 1 by 4. So I can say that area of the quadrant can be written as 1 by 4 into pi r squared. So 1 by 4 into 22 by 7 into r squared. The radius of the circle 14 into 14. So here I am simplifying to 14 7 times, 14 into 7, 98 plus 22 by 7 into half into 7 root 2 into 7 root 2. Root 2 becomes 2, gets cancelled with 2. 7 gets cancelled. So remaining is 22 into 7, which is 154. Now simplifying here, 22 and 4, 2 and 11 by 2 tables, and 7 will go in 14 2 times. So further 2 gets cancelled with this 2. So remaining will be 11 into 14, which is 154 along with the minus sign. Plus when 154 minus 154 gets cancelled, remaining is 98. So which will be the area of the shaded region. So I am writing 98 centimeter square. Hence I got the area of the shaded region as 98 centimeter square. Hereby, we have proved many problems using the tangent theorem, that is tangent drawn from an external point to a circle are equal, as well as the tangent is perpendicular to the radius through the point of contact. Also, we have seen area of related to circles. We have found the area of the shaded region for the given figures. Also, we have seen area of the sector, that is your minor sector and the major sector. We have given a formula for area of finding minor sector as well as a major sector.